today we are going to discuss about the logarithmic decrement. Okay, so you can see in this graph, this is a common type of displacement time graph. This is in the case of a damped oscillation, or I can say it is an under damped oscillation. So here we represent the displacement x. The initially at time t is equal to 0, the displacement was a0. Then at a particular time t1, the displacement reduced to a1. Then another time t2, the displacement reduced to a2. Then t3, a3, and like that the displacement is decreasing with respect to time. So we can say that this is an exponential decrease of an amplitude. I'm generally representing the amplitude. The initial amplitude was a0. So you can see at time t equal to 0, we got a0. Then at time t equal to 1, we got another amplitude a1. So which is equal to a 0 e raised to minus lambda t. So as the value of time changes, this thing changes. So a2 is equal to a0 e raised to minus lambda t2, and t2 is equal to 2t. I'm just simply writing 2t. So a2 is equal to a0 e raised to minus 2 lambda t. Then at the time t equal to t3, we will get a3 is equal to a0 e raised to minus 3 lambda t, etc. So generally we can represent the amplitude which is constantly decreasing with respect to time, or we can say that this is an exponential decrease, and we can represent that is initial amplitude is a0, taking that a0 by a1. What we will get? We will get a0 divided by a0 e raised to minus lambda t. So a0 cancel, we will get e raised to lambda t. Similarly, if we are taking a1 by a2, we will get a0 e raised to minus lambda t divided by a0 e raised to minus 2 lambda t. So a0 cancels, we will get e raised to minus lambda t into e raised to 2 lambda t, which is equal to again e raised to lambda t. Similarly, for any adjacent amplitudes, suppose we are taking the ratio of the amplitudes, only we are considering either the upper half cycle or the lower half cycle. If you are taking the upper half cycle, we need to consider all the upper half cycle. If we are taking the lower cycle, so we need to consider all the lower half cycle. So we can see that if suppose we are taking in the ratio of the amplitudes, we are getting something which is constant, which is lambda t. The logarithmic decrement, as per definition, it is the natural log of ratio of consecutive amplitudes. Okay. Suppose this is log to the base e, natural log of ratio of consecutive amplitude, that is log to the base a0 by a1 equal to log to the base a1 by a2 equal to log to the base e a2 by a3. Whatever we are taking, we will get log of e raised to lambda t, which is lambda t itself, and this is known as logarithmic decrement. So again that is the log, by definition, logarithmic decrement, which is the natural logarithm of the ratio of the consecutive amplitudes, is known as the logarithmic decrement. Next thing we need to study is the relaxation time. So next thing is relaxation time. So in the case of relaxation time, it is represented as tau. Okay. So the relaxation time, we can say that it is a time taken. Suppose initially we have an amplitude a0. Okay. And after a particular time, it will become a1, it will become a2, it will become a3, like that. Okay. So the relaxation time, by definition, it is the time taken to reduce the initial amplitudes to 1 by e times, or we can say the time taken to reduce the amplitude 1 by e times of its initial value, 1 by e, which we know that, which is equal to 0.368. So the time, that is the time taken to reduce a0 to 0.368 a0, is known as the relaxation time. This time, the time taken from here to here, is known as the relaxation time tau. and the equation is given by it is equal to m by b. As the damping increases, the relaxation time decreases. So the damping and the relaxation time is inversely proportional. That's why we can see for a very high damped oscillator, it will be suddenly drops to zero. In the case of moderate damping, we can see there will be some oscillation after a particular time that decays to zero. So as the damping increases, the relaxation time decreases. Or we already learned the equation of quality factor, which is equal to m omega by b. Okay, so we know that m by b is the relaxation time tau. So we can write the quality factor is equal to omega tau. That is the quality factor which is directly proportional to the natural angular frequency and the relaxation time tau. Or we can write the equation of the equation of a damped oscillation is d square x by dt square plus b by m dx by dt plus omega square x is equal to 0. This is the differential equation of a damped oscillation, and b by m, which is m by b is tau. So b by m is 1 by tau. So we can represent this equation as d square x by dt square plus 1 by tau dx by dt plus omega square x is equal to 0. This is also the representation of a damped harmonic oscillation.